All right, so I've just started recording. So we need continuous dynamic programming to tackle all these issues. So just a recap of how we did dynamic programming in the discrete systems. So we basically came up with this equation, which is basically the optimal cost to go. So J star is basically the optimal cost to go, and the optimal cost to go from every state is basically the cost that is going to take for the agent to move from its current state to its goal state. So that's how we describe the optimal cost to go. Or you could also call it the value function. That's what people in reinforcement learning call it. So the optimal cost to go, as defined by this equation, is basically the minimal action that results in, is basically the sum of the local cost. So this local cost, that's L of SIA, is basically the cost of performing the cost that's incurred when in state SI and an action A is taken. So that's the local cost. And then it's summed with the optimal cost to go. It's summed with the optimal cost to go. That's basically the cost that's incurred from the next state after executing action A in state SI. So you can think of F here as the state transition function, which basically tells us that if you're in state SI and you take action A, you end up in some state S prime. And so this basically represents S prime. And so this formulation of the optimal cost to go, or the optimal value function, was basically what we used to solve for the optimal policy, which we needed to perform optimal actions. So for instance, so if we had a grid world, I should have put a diagram of the grid world here, but then if we had a grid world where we are able to determine this function, this optimal value function for every single state, we can then derive the optimal policy or the optimal controller. The optimal controller basically tells us that when we are in this state, which actions should we take in order to incur the least amount of cost? Or put in another way, when we are in this state, what's the optimal action to take? And that's basically what we need from this whole system. And so that is where we ended up last week, by defining this optimal cost to go and explaining exactly what happens here. And so in the discrete case, we have F as a transition function, and it's usually represented as a lookup table because everything is discretized. We just have a lookup table, which basically has a columns of states and actions, and basically look up if you're in the states and we take this action, you're going to end up at some other state, and we then find the optimal cost to go for that state, sum it up with the current optimal cost to go for the current state. We then get the minimal cost, and we initialize that as the optimal cost for the specific state S we are trying to infer. So this is what we did for the discrete case. But we were only able to get this transition function because we discretized the system. So by performing the discretization, we basically came up with some lookup table where we can just look up if you're at this state and you perform this action, you're going to end up at some other state. And so in the discrete case, F was basically just a lookup table. But then if we are going to try to perform dynamic programming on a continuous system, we would want to, we don't discretize the system just as we did previously. So we'd have to consider the continuous transition function as itself without actually discretizing it. So in such a situation for continuous dynamic programming, we end up with a nonlinear cost function, simply because our cost function here could be nonlinear with respect to the system variables as well as the optimal cost function. They could also end up being nonlinear. And so if it's linear, if it ends up being linear, then it's okay. But then worst case is that it could end up being nonlinear. And because it's nonlinear, it's not going to be suitable for our purposes. It becomes a bit hard to use. And so what they usually do is that they basically approximate this nonlinear cost function, that's J. Yeah, they approximate this nonlinear cost function using first order Taylor expansion. So given this nonlinear cost function, that's basically J, which takes in some states x of n plus 1, they approximate this nonlinear cost function using Taylor expansion. So after performing Taylor expansion, we end up with this first order Taylor expansion where J of xn is basically the cost at some state xn, and then it's summed with some Jacobian, which is basically the derivative of the J, that's the derivative of the cost function at some point x, at some point at some other state s of n plus 1, where s of n plus 1 is basically represented as the transition function that's being acted at, transition function that represents that gives us the next state after action u is performed at state x. And so this is basically the first order linearization of this nonlinear cost function. So once you have this then we basically then replace. So we know d of j over d of t is basically that. So we basically replace this d of j over d of t with this formulation, and this gives us the cost function for. This gives us the linearized cost function for a continuous system. So once we've defined this linearized cost function for a continuous system, we then go on to examine the optimal value function or the optimal cost to go that we use for the we then go on to determine the optimal value function, because we need the optimal value function to basically tell us that to basically derive the optimal controller that we need to get the states to some desired states. And so at the beginning we talked about this optimal value function for the discrete case. And so with the same formulation in the continuous case, we basically have the same thing, basically where the optimal value function at some state x is basically the minimum, is basically the sum that causes the minimum cost of the local costs. That's basically locally in that state. What's the incurred cost when you take action x, and when you take action u at state x, and plus the optimal cost to go from the next state that you're going to end up after taking this action u on state x. So here LD is basically the local cost function for the discrete case. But since we've already derived the representation of the cost function in the continuous case, we basically replace this j with the new j we've derived here. We've linearized, that's basically the linearization. So we replace this cost function here with our linearization. It ends up being this more expanded equation, where this is basically the, and we also change the local cost function in the discrete case to the local cost function in the continuous case, where this cost function is a continuous function, and then the linearized version of the cost function. So once we have this, we can then perform some simplifications. So first, you notice that we have the optimal cost function here as well as outside. And so you could basically just, and because this optimal cost function doesn't depend on the action, or because it doesn't have any u attached to it, we could basically move it outside of this bracket or outside of this minimalization, and then subtract it from the optimal cost function here, and we'll basically end up with 0 here. So that's one simplification we can make. So once we make that simplification, we end up with the third equation, which is basically this. We could also realize that there is a dt here and a dt here, and we could basically factorize the dt out of this whole equation and then cancel it out with 0. And so we end up with this much simplified equation here, which basically states that 0, the minimum action that results from the from a local cost, from the sum of the local costs and the derivative of the optimal value function or the optimal cost to go multiplied by the next state is basically equal to 0. And so this equation right here does two things. It's one, it's simple, and it also specifies the conditions for optimality for a specific j, or a specific cost function j. So it basically states that if a cost function j star, or if the optimal, if some proposal cost function j is optimal, then its derivative multiplied by the next state plus the local costs at that particular state obtained from executing some action u it should be equal to 0. So it is this equation that is often called the Hamilton-Jacobi-Bellman equation. That's the HJB equation. So the main reason why this equation is important is that it specifies a sufficiency condition under which some cost function is going to be optimal in a continuous dynamical system. And so if you have some proposal cost function, if you come up with some proposal cost function and you want to know if it's optimal, you basically put it into this equation, and if it's equal to 0, then it's optimal. If it's not equal to 0, then it's not optimal. So this gives us a nice sufficiency condition. And given the sufficiency condition, and the second, that was the first benefit of this equation. And the second benefit is that it helps us to get the optimal policy or the optimal controller. So in reinforcement learning, they usually call it controller. They usually call it policy, but then in control theory, they call it controller. So within the talk, I'll probably be interchanging them. And in reinforcement learning, they also call the J star the optimal value function, but in controls, they call it the optimal cost to go. So I might be interchanging both terms as we go on, but I'll probably just call it cost to go and controller. So another benefit of this HJB equation is that it helps us to specify what the optimal controller is going to be. So the optimal controller is basically the optimal controller, basically the function of the controller is basically to tell us that when we are in some state X, which action do we take, which action U should we take. And so this, given this equation, we can then derive that when we are at some state X, the action we should take is the action that minimizes the sum of the local cost and the sum of the local cost with the derivative of the optimal cost to go multiplied by the next state you're going to end up in after we take an action U. So that's basically the optimal controller, and we can get this because we have the optimal cost to go, that's J star. So that's basically a very short description of the importance of the Bellman, of the Hamilton-Jacobi-Bellman equation. And later on, we'll use this equation to derive the LQR controller, which is a controller that's used in lots of systems, lots of robots like quadrotors and legged robots and all that stuff. And so we are now going to talk about the LQR controller. That's the linear quadratic regulator controller. And as the name says, the LQR controller has basically just two requirements, and the requirements are in the name, so it's not difficult to, it's not easy to forget them. So the LQR controller requires that in order for this controller to be viable for some problem, for some control problem, it requires the control problem to be represented by some linear system. So your system should be a linear system with linear dynamics. And linear dynamics is basically a system that can be described using some matrix, some ax plus bu is equal to some x dots or something. I'll show you what a linear system is in the next slide. So our system should be linear, and then the cost function should also be quadratic, both in terms of the states as well as the control. So if we can And we need the cost function to be quadratic, because if the cost function is quadratic, then optimization becomes easier, because if it's quadratic, then it means it's a U shape. And we know that if it's a U shape, then it has a global minima at the bottom. And so by having that global minima, it's basically a guarantee that the LQR controller is going to return the optimal controller for your system. So if your system has linear dynamics and you can come up with a quadratic cost function to get the system into some desired states, then LQR is probably the best controller you could use, because it's pretty simple and it's been successful in a number of systems. And so we're going to briefly go through, I only call it derivation. I guess it's a loose informal derivation of the LQR. So this is a linear system. So a linear system is basically a system that can be represented as x dot is equal to ax plus bu, where x is the system's dynamics, is the system's is the state's variables, and u is the control, and u is the control input. So for example, if you want to control a pendulum, x is going to be the basically the x is going to be the what's it called, the orientation, s is going to be the orientation, as well as the orientation of the joints of the pendulum, or basically the angular displacement. Yeah, that's the word. The angular displacement of the pendulum, as well as the angular velocity of the pendulum. So so x is basically the variables, the state variables that you need to describe your system. And so for simple systems like the simple pendulum, you can just represent x by basically the angular displacement and the angular velocity of the pendulum, because that's all we need to describe the pendulum. And for much more complex systems, like say a humanoid robots, like the Atlas robot from Boston Dynamics, it's reported that they had the state variables were like 36 dimensional. That means there were like 36 different variables that represented the states that were used to describe the state. And so it grows in complexity. And A is basically a matrix that represents so we call it a state matrix, which basically is basically a utility matrix to basically represent how much weight is given to each of the components of your state variables. So it usually depends on your system. So if you define your system, you have to come up with some A that's multiplied by some X. And U here, as I said earlier, is the control input. So for instance, if you want to control a pendulum, your control input is probably going to be some torque that's applied to the joints of the pendulum. And if it's a 36-degree of freedom robot like the Atlas, your control is probably going to be some 40-dimensional or whatever, or however many dimensions of controls or control points you're going to, or how many different controls you're going to exert on the system in order to get it to act the way you want it to act. So I would think if we assume that every joint has its own motor, there could probably be like 36 different dimensions for this control vector. And the B matrix also basically is basically a weighting matrix for each of the dimensions. So this linear system basically tells us that x dot is basically the change in the state. So if the if the state is changed, if we have a state vector x with some system matrix A, and we apply some control u to it, we end up changing the state by this x dot. So this is a very succinct way of describing some system, and it's a linear system because it's linear. The system is basically linear. It's basically something plus something, and there are no, it's basically linear. There are no like squares or square roots or anything like that. So this is a simple linear first order differential equation. Is also linear. And the next specification to apply LQR is that your cost function should be quadratic. So we represent the cost function L of xu, where this basically states that when you're at state x and you exit action u, you're going to end up with some cost L of xu. And this is also quadratic because x times x squared. So x is basically the state variables, and u is basically the actions, the control action or control inputs. And then Q here is basically a way to weight how much your control inputs, sorry, how much your state variables affect the cost function. And R is also a matrix to represent how much your control inputs affect the cost function. So it's up to the designer of the control system to decide which Q, the components of this Q matrix and this R matrix should be. And the only constraints on the Q and R matrix are that, of course, they should have the dimensions that satisfy this X transpose QX. So basically, if X is a two-dimensional vector, Q should probably be a 2x2 or something. So it's basically to ensure that you basically have to ensure that the Q has the right dimension as well as the R. And the only constraints are that, yeah, and of course they're supposed to be symmetric. They're also supposed to be symmetric and square matrices as well. So R here should be symmetric in that the R should be equal to R transpose, and it should also be positive definite. That's the eigenvalue should all be strictly positive. And Q should also be symmetric in that the Q should be equal to Q transpose. And it should also be positive semi-definite. So eigenvalues could either be 0 or positive. So those are the conditions on these. So on this dynamical system. So this is a linear dynamical system with a linear system and a quadratic cost, and that satisfies all the conditions necessary for LQR to function. So for such a system, I skipped a couple of equations here, but I could add I'll put a link to the main source on Slack if you're interested. But given such a system, we can, because the cost is quadratic, we could end up our optimal cost to go is also going to end up being quadratic with respect to the states, where the S is basically some positive semi-definite matrix that would have to find out later on what exactly it is. But then we could represent the optimal cost to go by some quadratic expression X transpose S of Sx. And then given this.
The question.
Yeah.
So the S essentially will be composed by AB and QR, right?
Yeah. Yeah. It's going to be composed of.
Oh, okay. Yeah. And the LXU is intuitively that's like the immediate cost.
Yeah, exactly.
The action. Okay.
Yeah.
So in this particular formulation, the term depends on X and U separately. So it's almost like the effect of U doesn't really depend on the X for that immediate cost. Is that the right way to interpret it?
The effects of the U, do you mean the?
Sorry, the not effect, but like the cost that's induced by U in a particular state is almost like independent of the state given this formulation.
Independent of the state.
Because the X and U here are separate in that summation here. Like Q is governing the X, R is governing the U.
Yeah. So it's basically a way to express the cost as a function of X and U, where Q basically determines how much weight you put on the X and R determines how much weight you put on the U. But then independence, I don't know. I've not really thought about it, so I can't say if they are independent or not. But I would think if you're in some state and you take some action in that state, the cost you incur also depends on the state, right? Because if you're in some other state and you take the same action, you're going to get a different cost.
Yeah, that's why that's why like I feel like this particular formulation doesn't express, it is not able to express that, right? Because the x and u are basically separate here for the L, for the immediate cost.
Yeah, yeah.
For the accumulated cost, it will, because the transition function
Yeah,
will change.
yeah.
For the immediate ones, yeah. Okay, just to make sure.
Yeah. So so we can express the optimal cost to go using this quadratic expression where S is some S we're going to think about later on. And given this expression, we can then insert this expression back into the HJB, the Hamilton-Jacobi-Bellman equation. And once we insert that J into this function, we'll end up with, I should have added equations to basically go step by step, but then once we insert this J expression into the HJB, we'll end up with the optimal action or the optimal control, which is going to be expressed as negative of R times B transpose times S times X. And usually because R, B, and S are usually just matrices, and all we need is the only variable here is the X. After solving the whole controller, we could then represent all of them by just some K. And so to make it simple, it basically represents the optimal action as the negative of K times X. And so how do we get the S? So as I said earlier, since we already have an expression for J star as this, we could then put J star into this Hamilton-Jacobi, I'll just call it HJB. We could then insert the J star into HJB as well as the expression for the immediate cost L, and end up with this formulation. So this basically tells us that when you find the derivative of this J expression with respect to X, you're going to end up with 2xts because X is X squared. So this is just a simple thing. So once we put all this descriptions we've made here into this HJB equation, we end up with this big system, this big linear equation, and the stuff in brackets is called the Riccati equation. And so we could just cancel the stuff in brackets is called the Riccati equation, and this is equal to 0. So, but then we can then cancel out all the x's, and we end up with just this expression is equal to 0, and that's what they call the Riccati equation. And the Riccati equation is an important equation because LQR is important, and so in most numerical solvers like or numerical software packages like Matlab or Julia, or most of the packages that they use for controls, there's usually a dedicated function for solving the Riccati equation. And so it's basically something that's like people do a lot. So they have like very dedicated systems for solving this. And they usually solve this numerically because there could be some non-linearities involved. And so they usually solve it numerically using some optimization, but it's very complex. We don't need to go into the details. And so the goal when solving for the Riccati equation is basically we need a value of S that satisfies this equation. This is equal to 0. So we need some S that basically tells us that basically sets this whole thing to be equal to 0. And because we know that S, so because you can see that S here is quadratic here, like S squared, you can end up with some X squared, and this is not linear. It's a quadratic. They usually use numerical methods or some optimization to solve it. And so once you get the S, then we basically solved the system. We basically solved the linear system because once we have our S, once we solve for this S, we already know B because that's what we designed the B in describing our linear system. And we already know R because we designed the R to describe the cost function. So once you have S, you can then multiply all of these by the desired state X to get the optimal control U. So that's basically the LQR in summary. So LQR in summary is basically like finding this S value. So once we get an S, we can then multiply all of that by the desired state. So in the cat-pool problem that would look at, which code we'll look at later on in the next few slides, the desired X is basically such that the angular displacement of the pendulum that's mounted on the cat should be equal to 90 degrees. That's basically that the pendulum is like straight up. And so that could be some desired X. And then we can then use this K to come up with a control that would send the state to that S, X. Yeah, and that basically sums up what I just said. So having this, we then solve it. And doing LQR in Matlab is like very simple. If you just use this, there's a function in Matlab called LQR. So if you want to use LQR for your dynamical system, you basically have to follow these few steps. You describe your system as a linear system, describe your A matrix, describe your B matrix, and then you then come up with some quadratic costs, describe some Q and R matrices, and then make sure all the dimensions match. And then once you have A, B, Q, and R, you can then pass A, B, Q, and R into the LQR function. And the LQR would basically return K and S, where K is basically the product of all of these, and S is just like the S. And so if you just want to get the optimal control, or the optimal action, you can then use the K to get the optimal action. But then if you want to perform some another analysis, you can use the S to get it. So that's basically LQR in summary. And so the next thing we're going to do is I'm going to go through some Matlab code where they solve for where they use LQR to solve the cat-pool problem. And I hope you can all see my Matlab. So the cat-pool problem is basically, as I said earlier, I think it's in the OpenAI gem. Let's see, OpenAI gem cat-pool. Where's cat-pool? I'm looking for an image. Looks like they've removed the image. The cat-pool is basically. How come there is no image? I mean, I checked this yesterday and there was an image. Oops. No, there's no image, but my Matlab simulation, well, it's not mine, but this Matlab code comes with cartoon, so you basically be able to see what happens. So before the cartoon, before I go through the code, I'm just going to run it so that you see what happens. Yeah, so this is a cat-pool, and it's moving on some one-dimensional track, and the goal is that the pendulum as attached to the cat-pool is basically 90 degrees with the surface of the cat-pool, or its angular orientation is like angular displacement is 90 degrees. So that's basically the goal, and it starts from some random initial position. So we could change the initial position in the code. So to use the code, we first the first step, as I said, was to describe your linear dynamical system. That's basically come up with the A matrix and the B matrices. That basically describe your system, or that basically makes everything. That basically describe your linear system. So we could so for the pendulum, there is a way to derive this A matrix, but then there's a way to derive this A matrix from the actual like dynamics equations of a pendulum, where you then consider the mass, the gravity, and sine theta and all that stuff. But I could include sources to it if you're interested. But that's like undergrad level controls systems course. So we could skip that. And so to design the A matrix, we basically need the mass. So M here, lowercase m here is the mass of the small ball on top of the pendulum, and uppercase M here is the mass of the cat itself, and L is the length of the pendulum. G is acceleration due to gravity. It's -10 because it's pointing downwards. Yeah, and D is, I think, what was D? I think D is the is the distance, maximum distance can move or something, but I'm not sure. What was D is probably the length of probably the width of the cat itself. And B is and the pendulum is up, B is equal to 1. That's basically it's used to compose the B matrix for the control. So given these parameters, we then set up the A matrix. So there's a systematic way of deriving this A matrix. So this is basically like two linear equations that we formulate into this 4x4 matrix. But that's undergrad control systems scores. So once we get the A matrix here, we can then also get the B matrix, and this we also design. This we also get from the dynamics equations. So we've now specified our A matrix and D matrix, and we have to ensure that the A matrix is and then you have to ensure that the A matrix has like correct eigenvalues, as well as the A matrix has eigenvalues, meaning it's invertible, as well as ensure that the system is controllable. So controllability is some other system. I think we might talk about it next week, but this is basically like safety checks to make sure that this is a valid linear system. So once you've described the linear system, we then decide the Q and R. So the next step is to decide the Q and R matrices in the quadratic cost function. So here they took the simple route to basically, so it's up to you to decide what the Q and R should be. So Q here is basically just an identity function, a 4x4 identity matrix. Sorry, it's a 4x4 identity matrix, and R is basically as small as possible. And this basically means that if we go back to the quadratic cost function, if Q is identity, then it means that the cost for each of the dimensions of the states. So X is basically a 4-dimensional vector. So it means that each of the 4 dimensions of the state variables that describe the states of the system are equally responsible for the costs. And so you could basically alter these to change the behavior of your controller. So if, for instance, you don't want the orientation of the pendulum to become too small or too big, you could basically reduce the weight on the orientation parameter of the state variables using this Q matrix. So this Q matrix is basically like a way to weight the various state variables, and R matrix is basically telling us how much weight are you going to give to the control on the control input. So for instance, if you don't want the robot to move extremely fast, you want to reduce the speed of the robots, you can then make R like extremely small, so that the cost is not the cost of the is not that dependent on the robot speed. And so we basically designed a Q and R to have some attributes that we want the system to have. And then after determining the A, B, Q, and R, we basically just call this line to get to basically solve for LQR. So it's as simple as that. So here we don't need the S, so we basically just we basically just return the K. So K is equal to LQR of A, B, Q, and R, and this K is basically the K here that we can then multiply by the desired state to get the optimal control inputs, and it's as simple as that. So that's like a nice thing about Matlab, even though it's not free. It has these nice tools where you can then just call it. And so in this LQR, you can imagine that the Riccati equation is being solved in the background to get the S, and then the S is then used to get the K, and then the K is returned. And so everything else here is basically just simulation stuff. So once we get the K, we can then multiply. So here we basically define the time steps, and then this is the initial condition. That's basically the initial state. And so here, I think the third input in this vector basically describes the orientation. Yeah. So the vector is basically made up of x dot, q, and q dot. So x is basically the position of the cat along the number line or along the one-dimensional track, and x dot is the velocity of the cat. And q is basically the orientation or the angular displacement of the pendulum that's resting on the cat, and q dot is the angular velocity of the pendulum. So this initial condition basically tells us that the position of the cat is at some -1 distance from the origin, which is basically somewhere around the left end. And so I'm going to run it again. Yeah, so it starts somewhere at -1, which is at the left end. And let me just close it. And yeah, so that's the first. And the second is basically the velocity is 0. And the initial orientation is basically pi plus 0.1. So that means it's somewhat a bit inclined. The pendulum is a bit inclined at the initial condition, at the start. And then the velocity is 0. That means it's static. So that's the initial condition. And we could probably change these to, and we could see the resulting effects in the simulation. And then WR here is the reference position. That's basically the goal or the desired position we want the system to be in. Meaning we basically want the system to end up in a way such that the cat itself is at position 1 on the number line. It's static. That means its x dot is 0, meaning it's not moving. Pi is basically the angular displacement of the pendulum. So the pendulum is like vertically on top of the cat, and 0 means that the pendulum is also not moving. So that's our desired reference position. And so our controller is basically, so there's an anonymous function in Matlab. So this is basically the minus kx. So but then instead of passing x here, we then, yeah. So this is basically minus kx. So this basically describes the function for basically the control. So our control inputs, so k basically is not exactly taking x, but it's taking the difference between the current state and the desired state. So that's a trivial thing to specify here. So this is a function that's the u function, or you could call it the optimal policy or the optimal controller. So this u here represents the optimal controller. So it takes in an x as input, and then as output it multiplies -k times the difference between the input and the goal position or the reference position. And so that's basically our optimal controller. And then we then run the simulation to get we run the simulation in for 10 seconds. So this is basically the time step, and each time step is 0.001 seconds. And then once we have all of these, we then draw it in the simulation, or basically display it in the animation. And then these are like some other examples with some different initial conditions and all of that stuff, just to get some plots. But we don't really care about that. So once I'm gonna run this thing again. So it starts at that initial position, and then the control is basically, so the only thing the controller is controlling is the position of the cat. The controller doesn't control the pendulum. It only controls the position of the cat. And so this system is an under-actuated system, because unactuated systems are systems where like some parts are being controlled and some parts have no actuators. And so the only control that's been exerted is the position of the cat, but then it's moving such that the pendulum is stable. So I think if you've gone to a carnival before, there's usually like the clowns usually try to balance some stick on top of their hands or something, or balance stuff on their head. So this is basically a balancing problem. And then so we could also change the initial condition. So the initial conditions specified here are very nice, and so from that initial condition, you can then end up with some nice solution. But then, if we make it extremely terrible, such that it's probably not gonna work. Let's see let's see what happens. So instead of 0.1 pi plus 0.1, we could make it, I don't know, 0.5, and this is probably gonna fail. But let's see what happens. So this is basically the initial orientation of the pendulum. So even with this, it's still able to recover somewhat. Yeah, it ends up at position 1. So that's nice. Let's increase it to, oh, it's finished. Let's increase it to say 1.5. I want it to fail. So there are some initial conditions where it's not possible to come up with a controller because the system is underactuated. You can only control the system up to some points. At some regions, it's not going to be able to get into your desired position. So
Question.
Yeah.
Why I still couldn't quite get in line 33. Why is it as straightforward as just to replace x as x minus the target x?
So that's basically how the so theoretically it's just going to be x, but then in order to use this ODE45 simulator, the position should be the difference between the current state and the reference. So it's just an artifact of this ODE45 simulator.
But just regardless of the ODE45, but if you just look at originally how you derive the Hjb, there is so far there is no place where we're saying what is the target x, right?
Yeah. So in this formulation, the x here is the target x. So the x here is the target. So yeah.
Oh wait, let's see. I thought the x is the current x. Like if you go back to earlier slides where you derive the J star to like before the LQR.
For the LQR.
Alfonso, I'm sorry to interrupt. I need to take off. Thank you so much.
Sure.
See you, Jorge.
See you. Nice to see you. Bye-bye.
Nice to see you.
Yeah.
Bye. So yeah, so for example here, yeah, like even before this, like before Hjb equation derivation, like everything here about x is the current x, right?
Yeah.
Like this is not about target x.
Yeah. Here's the current x. So in this formulation, I skipped a lot of steps just to make things more concise. But yeah, I could. It's probably that controller. There are some variables here that are overloaded. So up to this point, the x's are all the current x. But then in order to set up the optimal controller to get to some targets, the optimal controller is basically the controller that's going to take us to some desired goal based on some current information. So I think, yeah, I'm probably thinking about it currently. I'm probably confusing the two. So the optimal controller should take us to the desired position, regardless of where we are in the state. And so I guess here, in this case, I think the x is the current x. Sorry. So in this case, x is the current x, but then the optimal controller has the information of the desired position already embedded in it, because that's how you derive the optimal controller, by controlling it to go to some specific state. So
right. So if we go all the way back to the Hjb, so in a generic context,
HJB,
I'm just trying to understand is even without the context of LQR. So in this case, if we have, let's say, if we have a target x, how are we gonna embed that x in this equation so that we can derive the optimal pi
So here we don't talk about the target because we know that so the target here is embedded in this optimal cost function, because the optimal cost function should go to some specific
I
state.
see. I see. I see.
Yeah.
I see. I see. That makes sense now. So it's really boils down to where. Wait. Let me think. It really boils down to where the immediate cost becomes 0. For the x.
Yeah. So the immediate
Like
cost is 0 at the desired position.
right. For certain u, right? For certain action. Okay.
Yeah.
Okay.
So,
Okay.
sorry for the confusion. So this is the current x, but then the goal x is embedded in the optimal control. Is it
So
running?
the way to embed the target. So for example, in this slide, the way to embed the target x in is really just to say when x is equal to the target x, the lowercase l of x given u equal to 0 will be equal to 0.
Yeah. That's like
Like
something.
the way to.
Like,
Okay.
yeah, that's I should have spoken about it last week, but that's like how the value equation is derived. Like it usually starts from the goal position, and at the goal position the current cost is 0, and then it moves one step outwards, and then the cost then starts building up. I should have
I see. And
included the graphics, but yeah.
And a quick question, is there any way to impose any constraint on the states here? Like the boundaries, basically, like
Yeah.
imagine there is a constraint workspace for the cart.
Yeah, I know what you mean. In this case, we are considering unbounded actions, but then there's probably a way to specify conditions for the state for the actions or for the states. Basically, the cart shouldn't exceed the current space that's given to it. There's a way
Right.
to do that. There's a way to do that. I don't really specify it in these equations because just to make things simpler. But yeah.
And another stretch question, just in case you happen to know about, are the bipedal locomotion stuff also mainly built on LQR systems, or is much complex than that?
Yeah, so for the control, they mostly use LQR for the control itself, but in order to work, they'd have to perform footstep planning. That's basically plan exactly where the robot's leg should stand. So that ends up becoming the desired state.
I see.
We can then use some LQR like this to basically solve from the robot's current leg configuration to the goal configuration.
I see.
Yeah.
I see. So the challenging part for them isn't really the LQR controller. It's really more of the gait and the foot location planning.
And I would guess with their linearization of the states probably also takes some efforts because LQR requires a linear state and their system is like extremely non-linear. So I have to put some work into making LQR work for their system.
I see. And also, so far we haven't added any noise into the control, so that would also raise the complexity to a different level.
Yeah, but then I would say because the system is kind of like a feedback system, as in giving some current states, we then get some action. We don't really care about noise because we already know that if we end up in some wrong states, the optimal controller should come up with some actions that would take us back to the current state. So a robust controller should be robust to noise in the joints and all of that stuff.
I see. Makes sense. Thanks.
Yeah, it looks like the initial position I give it is giving the LQR a hard time to optimize. So it's still optimizing and cancel it. So yeah, so 1.5 was probably too much. I could probably make it, I don't know, one more initial position, then we'll move on. So there's one more. Yeah, so you realize that here the initial position of the pendulum was a bit more tilted than initially, but it's still able to recover. probably the reason why when I made it 1.5, it was taking a lot of time was probably because the space it has is probably too small to be able to like move and recover its current position. So yeah, so this graph is basically a graph of the state variables. So as I said earlier, the state variables are it's a 4-dimensional state where x is the position, v is the linear velocity, theta is the angular displacement, and omega is the angular velocity. So this is basically the how the various state variables were changing along the along that horizon when it was trying to balance itself. So that's a simple visualization. So so that's it for LQR demo. I could send this. I could send a link to this Matlab script if anyone is interested. And so the last subtopic we talk about is oh yeah, so in the real world, LQR was actually used to get this plane to pitch on a string. So this was back in 2010 at MIT Rastedrick's lab. I'm just gonna let this play. So this is all LQR. So I'm guessing the state variable is probably going to be the orientation of the plane itself, as well as the orientation of the ailerons or the stuff that changes the orientation of the plane. And the desired state is probably, I don't know, it should be in that position or something with that orientation. And then they are probably getting some feedback from a camera mounted somewhere that's basically telling the system the current position of the plane or something. I've not really read a paper, but that's just I guess. And the goal is to get the plane to pitch on that string. I thought this was really cool, and it's all just LQR by linearizing the system. And then this is basically I think this answers your question, Jen, about the noise. They are blowing air on the robot to make it shaky, but it's still able to perform this. So this was from 2010, so that's cool. And there's also a video of Atlas. It's a longer video, but in the DARPA Robotics Challenge in 2015, Atlas was running LQR for its controls. All the controls is basically LQR. Yeah, and that's Rastedrick. He's the lead guy. And yeah, so that's him. And that's the assimilation system. So it's pretty cool. LQR is like, even though it's really simple, what you really need to do is be able to describe your states as a linear system and come up with a quadratic cost, and everything else is just engineering. Yeah, so the last thing we talk about, I'll go through this briefly, is function approximation with value iteration. So what we did LQR right now, what we just did LQR is one way of solving the system, of solving for optimal controller for the system in a continuous, when it's a continuous system. But then there are some instances where you probably just, if it's a linear, if it's a discretized system, you'd probably want to, and you basically just want to come up with a way of solving for the optimal cost to go with some form of function approximation. You could, so this is basically an alternative to using the LQR, and this is basically an alternative. And so what you usually do is you start by approximating the optimal cost to go with some J that depends on some parameters alpha. So this J, so our goal here is to use a function approximator, like say a neural network or some or some regression, or some least squares regression or something, some polynomial to represent the cost function. So here we approximate the optimal cost function, optimal cost to go as parameterized function that has parameters alpha, and the goal is to optimize. The goal is to basically use gradient descent or some form of least squares optimization to get the parameters for this cost function. And so what they usually do is that so originally this is the optimal cost to go. It's basically a minimization of the sum of all the costs for all the states, and it's the initial state is x0 and it has some transition function f. But then we want to approximate, we want to get this value function that has these parameters, and so we can solve that using least squares or some form of approximation or some form of estimation process where we get some desired JD, which is basically they call it the target network, which is basically some neural network. So when people use neural networks to do reinforcement learning, so this is basically a variation of like reinforcement learning. I think it's called Q-learning or whatever. So they basically get some target neural network, and then the goal is to minimize the costs of this JD. The goal is to minimize this cost such that we can end up with some parameters alpha that enables this J of alpha to approximate or get closer and closer to the J star. And yeah, so that's basically it. So once they formulate it as this, they then use some gradient descent. So in neural, you could either use a linear you could either use least squares. This is basically a least squares formulation, this alpha here. But then instead of this, people could also use gradient descent using their favorite optimizer, like say, I don't know, stochastic gradient descent or whatever, to come up with a gradient between the desired costs as well, desired cost and the J alpha. So J alpha is basically an approximation of the optimal cost, and then they basically once they get this difference, they then update both JD and J alpha, and they keep doing this. I don't really know much about the details of this because I didn't read this part much very well, but on a higher level, that's basically what they do for so this is what they usually call Q learning. So the Q function in reinforcement learning is basically the value function, and how to learn this value function is they usually formulate it as something like this. And so once they get a parameter, so these parameters are going to be the parameters of the neural network. And so they'll end up with a neural network, which is basically a functional approximator, which has alpha, which are basically the parameters of this Q function. And then they use this approximation of the optimal cost function to get the optimal controller. And then they use the optimal controller to perform actions in the world. So this is basically what reinforcement learning, deep reinforcement learning tries to do. And so this is like a way to link that with what LQR is trying to do. And so the benefits of this is that because they use some form of discretization and functional approximation, they don't really need a lot of knowledge about the system. Whereas in LQR, where we had to solve the Riccati equation and do lots of differential equations and stuff, here all they need to do is basically represent it as a neural network and then perform some optimization to get the best parameters for this Q function or the value function. And then they use that to execute actions in the role. And this ends up being sometimes unstable, just like reinforcement learning is unstable, mostly because they don't really account for the dynamics and because they perform that discretization. But then I'm pretty sure like more advanced methods of like in deep reinforcement learning probably do a variation of the two. I'm not really familiar with that literature, so yeah. And they call it the fitted value iteration method or Q learning basically. So this was an old idea, which was not very viable because this function approximator was not very good. But then with the incoming of like lots of deep learning systems and deep learning algorithms, it's made the learning of this Q function easier. And so that's what people usually do now these days and call it reinforcement learning, as well as some new things they've added to it. So that's like a link to what Q learning does or reinforcement does as compared to LQR. And so there are different formulations and extensions of LQR. So next week, if no one signs up for a reading group, we're going to talk about the various variations of LQR, and we'll go more into more details about how to get the plane to do the pitching on the rope pin. We'll go into more details about how they got this thing to work, this plane thing to work. And we're going to do all of that next week. And yeah, that's it for reading group for this week. And there's also some code for the for using that fitted value iteration Q-learning stuff to perform to solve the double integrator problem we tackled last week. And I'm not going to go into this because we're already running out of time, but yeah, I could send a link to this Google Colab script if anyone is interested. All right, thank you. I'm done.
Thank you, Alphonsus.
Thank you.
Yeah, thank you.
All right, see you next week.
See you.
Hi, thanks, Alphonsus.
Thanks, Yana.